Alright, so today we're going to be starting with acid-base balance, and I decided to go ahead, again, because of the content, I'm splitting this into two different lectures. It just makes it easier to download and upload it to YouTube and that. And plus we do have time. I looked at the schedule. So this is probably, I'm trying to think, we did our inorganic and organic. I think there's some stuff on the test tomorrow for that, for Friday. So this is Friday's lecture. This stuff will be on exam 2 for next week Friday, which would be the 15th. This is going to be in a totally different language. It's going to be challenging, to say the least, to grasp this concept. I have included several links on the day for this course, for day, I think this is under day 6. So definitely utilize all those links. So anything that's under this acid-base day, because it's basically your last day for chemistry. Yeah, it is day 6. So it really will include day 6 and day 7. So this will be Friday and Monday's lecture. So chapter 14 in Egan is where this came from, and like I said, if you try to read that, you will think it's Greek. Some of it will hopefully make sense, but you know, look at it, highlight it, go back over it after the lecture. And I did include 2 different links that are you know, more readable text-like links. The one that I mentioned with that Lane, L-A-N-E-C-C, or I don't know, I have to look really quick, I'm sorry. Yeah, media, lanecc.edu. Some of those pictures actually come right out of Egan, so they're using Egan's as a resource too. So hopefully that can help you. There's also the one from the NCBI, lmn.nih.gov article, and I had students tell me that that was helpful. And also there's 2 YouTube videos, so don't beat yourself up. You're not going to get this the first time, okay? And we continue to talk about this throughout the whole entire program, okay? And it'll become more and more familiar the more you hear it. All right, so with that being said, moving on. So we're just first of all going to be talking about pH. So the pH scale and the pH of your blood. So ideally we like to have pH in a perfect world at 7.4, okay, in your blood pH. Okay, so we draw blood gases. That's part of our job as a respiratory therapist. It's a blood draw out of the artery. Generally we draw those blood gases from the wrist, so where you feel your pulse in your wrist, that's your radial artery, and that is the most ideal site to draw gas from. The other place that we can get a blood gas if the patient's pulse isn't the strongest is the brachial, and so that's in the inside of your elbow area. And during a code situation, we sometimes have to get them from the femoral, which is in the groin. Depending on a lot of times physicians will decide to go for those, just because if you did some damage there, you have like a whole leg that you could potentially risk having circulatory issues with. But generally if somebody's coding, that's probably the least of their worries at the time. But you know, it depends. It's a nice big fat artery, but it's very deep, so you usually bury your needle to the hub. So most of the time a physician is fine. They'll just go ahead and get it. So so the pH is one of the numbers that we look at during a blood gas, okay? And so the range is 7.35 to 7.45. So if we're somewhere in that range, we're generally pretty happy, but just knowing that 7.4 is your, you know, textbook perfect ABG pH value. So all of the cells in our body depend on this to, you know, to keep everything regulating, homeostatic regulation, so everything's happy. And we have some amazing mechanisms in our body to help regulate that pH. Our breathing, so if you're taking notes, I'm just going to start, really basic here so you can kind of refer back to it. So your breathing is in control basically of your CO2, your carbon dioxide, okay? And then your kidneys and then other buffers within your body are kind of more in charge of the bicarb. So bicarb, and that's actually HCO3, the subscript of 3 in a negative ion. Okay, so HCO3 with the negative. Okay, and you'll see that. And then hydrogen is just an H with a positive. Okay, but you'll see that here coming up in a couple slides. So it's very critical that we keep that pH within the range of 7.35. Oh, that's a typo there. It should be 7.45. I will have to fix that. Okay. All right. So there you can see the hydrogen. Even small changes in the hydrogen ion concentration can cause vital metabolic processes in the body to fail. Okay. So acid-base balance is what keeps those hydrogen ions in normal range. So when you think of hydrogen, just kind of associate hydrogen with acid. Okay, hydrogen makes us more acidic. So if we have more hydrogen, we're going to be more acidic. Okay, and acidic on the pH scale is then less than 7.4. So 7.4 is that kind of middle area. And so if it's less than 7.4, it's considered more acidotic. If it's to the right, I guess, or more than 7.4, then you're more base. Okay. Again, though, we'll be okay if the 7.35 to 7.45 range. So we have 3 major organs, basically, that help regulate this acid base level. You might also hear it as alkaline, as for base. So the lungs, the blood, and the kidneys. So when you think of kidneys, kidneys are kind of in charge of the bicarb. All right, and this is just a quick little picture here, kind of showing you, oh, sorry. Hey, to stop. All right, sorry, I had the interruption of my dogs. This picture here is just illustrating the different ranges of pHs. There's a similar picture in your A&P book on page 38 showing how base being extremely on the base, bleach being on the extremely basic side with a pH of 14. And then, as you can see, blood being in the middle at about 7.4, and then pH of 0 being extremely acidic would be your battery acid and hydrochloric acid, and kind of different materials there, substances in between. Okay, so again, as the concentration then of hydrogen ions increases, so as you get more of the H+ increases in a solution or in blood, you become more acidic, okay? Meaning your pH decreases. So you need to know that. You need to know pH decreases with being acidic, okay? Decreasing meaning below 7.4, or just going down in general, okay? As the level of hydroxide ions, on the other hand, increase, okay, and this has to do with your bicarb too, increases, then you become more basic or alkaline, and then your pH increases, okay? So get those two concepts straight in your head, okay? So with 7 being kind of neutral, then if the pH is considered acidic, it's going to have more hydrogen ions than hydroxide ions. And then the flip-flop is the other way. If a solution has a pH of 6, it actually has 10 times more hydrogen ions than with a solution of a pH of 7. Okay, so that's kind of like the ratio there. for every degree of a change in pH by one number there, you would have 10 times the increase of hydroxide or hydrogen ions, your H. Okay, so anytime your hydrogen ions go up, your pH is going to go down and you're going to become acidic. Okay, if your pH goes up, then that means you have more hydroxide ions and you become more basic or alkaline as your pH increases. And we just want to be somewhere in that, again, that 7.35 to 7.45 range. You need to know those numbers, okay? And that's part of your assignment in EGANS. All right, so CO2, carbon dioxide transport. CO2 diffuses out of the cell and is transported in the blood in different ways. So less than 10% of it is actually dissolved in the plasma. About 20% of it binds to hemoglobin. And I just wrote hemoglobin HGB or HB. That's generally the abbreviations that you'll see for hemoglobin. As you get more into the course, we kind of tend to get lazy and we write out things with a lot of abbreviations. So you probably have already seen that in anatomy and physiology perhaps. But so if you see HGB, that's kind of, I don't know if that's more old school, that's kind of how I always have done it, but it seems like HB is used probably more, I guess, now. So they both mean hemoglobin, okay? And then the majority of the CO2, 70% of it, is converted to carbonic acid, and that's to be carried in the lungs and to be eventually exhaled, okay, as a gas. Okay, so when we talk about all of our lovely balancing of equations, this equation is continually going back, or it's really a reaction that's going back and forth all the time in our bodies, okay? So you're going to want to know this equation. You'll hit it hard again with Derek, again in mechanical ventilation. You will see it over and over. All right, water break. Okay, so again, we want to keep the acid-base balance is what helps keep the pH or the hydrogen ions in normal range. That number, we just can't say it enough times, but you need to know that. So hydrogen ions formed in the body come either from a volatile or fixed, which is also considered non-volatile acid. So volatile acids are in equilibrium with a dissolved gas. And if you look at this PowerPoint in a regular format, so if you go back to it and look at it in the way you view it in the class, not through the YouTube link, you'll be able to see some little notes that are underneath. Like, I forget what we call those. I'm drawing a blank. So those are your presenter notes, okay? So the only volatile acid of really physiologic importance in the body is the carbonic acid. And the carbonic acid there is right in the middle, your H2CO3, okay? Which is then in equilibrium with dissolved CO2, which is being demonstrated in the CO2 hydration reaction, which is this equation is known as the CO2 hydration reaction. Okay, this is happening during aerobic metabolism, which under general normal circumstances generates approximately 13,000 millimoles per liter of carbon dioxide each day, which produces an equal amount of hydrogen ions shown by the equation. Okay, so know that this is your CO2 hydration reaction. Okay, and the reaction is constantly moving back and forth. Okay, so you have CO2 and water combined together, turn into carbonic acid, and then it breaks down, and then you have, there's your bicarbonate and then your hydrogen ion. that was what I was talking about before, your HCO3 with the little negative, and then your hydrogen positive, okay? And we'll talk more about this. So, the little asterisk then has to do with that, those speaker notes there that are on the bottom. So if you view it, I'm just looking at it on my other computer so you can to make sure that they're definitely there. So the tissue metabolism then produces vast amounts, lots of CO2, which is then hydrolyzed into the volatile acid of carbonic acid. Like I said, this is going to be kind of very Greek for a little bit, but just kind of hang on. I definitely believe that those other links that I have for you, especially the YouTube video links, I think they're helpful because they start drawing things out a little bit more as they're talking, and I don't know, just different ways of learning it. Alright, so as you saw back in that previous equation, there was carbonic anhydrase, okay, and that is an enzyme, okay. Just get used to anything that has ASE, that ends in ASE, is generally an enzyme. And an enzyme is a catalyst, okay, so it speeds up what's going to happen. And I believe we spoke about that when we were talking about how we can get chemical reactions to happen faster. You can increase your concentration, you can add heat, or you can add a catalyst. Okay, so carbonic anhydrase is the catalyst in this reaction. Okay, so as the CO2 diffuses into the blood at that tissue level, this reaction is going to occur, and it happens mainly in the red blood cell. And another name for red blood cell is erythrocytes. Okay, I'm sure you've learned that in A&P. So again, carbonic anhydrase is an enzyme that is present in the red blood cells, which helps aid in that conversion of CO2 to the carbonic acid and bicarbonate ions. Okay, so that carbonic anhydrase then helps aid in the conversion of CO2 to carbonic acid and bicarbonate ions. When the red blood cells then reach the lungs, that same enzyme then helps convert the bicarbonate ions back then to CO2. So that's why I'm saying this reaction kind of goes back and forth. So the CO2 then is that's how we that's what we breathe out. Obviously, we exhale the CO2. Okay. So and again, that carbonic anhydrase, that's our catalyst, which can actually increase the rate of this conversion about 13,000 more times. All right. So hydrogen ion regulation in the bodily fluids. So we're still continuing to talk about this, and we're talking about different ways the body keeps the pH constant regardless of how much CO2 is produced. Okay, so I just want to say as a kind of a side note, if you think about it, when you're not breathing, okay, if you're not breathing sufficiently enough, your carbon dioxide is going to go up. Okay, you're going to have an increased CO2 if we're not breathing. Okay, and if we're not breathing, our CO2 goes up, which also means our hydrogen ions go up, and we become more acidic. Okay, so as our CO2 goes up, we become more acidic. So think for just a minute about things, disease processes, or situations that might happen where your carbon dioxide is going to go up. Things that we would have to deal with. Okay, so there are several of them, but just a couple things that I'll throw out there. You know, disease processes like asthma. You have a bad asthma attack and you're not able to breathe efficiently, you're not able to get rid of that carbon dioxide, you'll become more acidic. For any reason that you were to stop breathing, let's say you had a head injury from a car accident or a stroke, or possibly a drug overdose, which unfortunately we see a lot of, or alcohol overdose. Those people stop breathing, or they don't breathe as effectively, so their carbon dioxide level goes up and they become more acidic. So then that's when we jump in. That's our job, to help bring that CO2 level back down to help normalize the pH. Okay, so ventilation is one of them that's mentioned there. Two of the major ways that the body helps keep the blood's pH constant regardless of how much CO2 is produced. Well, obviously ventilation and isohydric buffering. Okay, isohydric buffering. So in isohydric buffering, most of the hydrogen produced this way actually doesn't really cause too much of a change in the pH, because the hemoglobin in the red blood cell helps buffer that hydrogen. Okay, and we'll talk more about that as we go on. So when we're looking at this equation here, we see that when the blood reaches the lungs, the hemoglobin releases the hydrogen to form CO2. So that's what we're kind of seeing. We're looking at the bottom and kind of working our way up and then to the left. So this way, the ventilation helps get rid of the carbonic acid just as fast as it's produced. So the hydrogen is carried then by a deoxygenated hemoglobin. That's what the HH actually means. HHB is actually a deoxygenated hemoglobin, and it is released as CO2 into the lungs. So lungs actually can remove greater quantities of fixed acid compared to the kidneys. Okay, so they're really responsible, the lungs are responsible to get rid of the fixed acids. In healthy people, the acid excretion mechanisms of the lungs and the kidneys are delicately balanced, so they kind of each do their own part. And kind of what happens is that if one part of the body is sick, like for example, if the lungs aren't doing their job, then the kidneys help compensate, and vice versa. Okay, it's kind of that delicately balancing act, trying to maintain homeostasis so that we don't go to haywire. Okay, so in people affected by disease or illness, failure then of one of these systems can be partially offset by a compensatory response to the other. And so as the CO2 rises, then like I said, we become more acidic. Then the bicarb actually helps to compensate. Unfortunately, it takes a long time for the bicarb to compensate, but the bicarb also will rise. So when you look at your pH and looking at acid and base, it's kind of opposite. Like CO2 rises, becomes more acidic. If bicarb rises, you become more basic. Okay, when your bicarb level drops, then you become acidic. But when your CO2 level drops, you become more basic. So it's a constant, like, you know, like a seesaw, kind of going up and down, trying to maintain an area of homeostasis where we can keep that pH in decent ranges. But we'll talk more about how that all happens as we go on, because it's quite complicated. Okay, so again, as we mentioned earlier, the hydrogen ions come from either volatile or fixed acids. Most of the hydrogen is a result of the catabolism, which is the breakdown of proteins. So know that term, catabolism, is the breakdown of proteins. And anaerobic metabolism produces lactic acid. Okay, so that's another contributing factor when you don't have any oxygen going on, or you think about your tissues not getting enough oxygen, and you build up that lactic acid, and that can be uncomfortable. Or it metabolizes fat. Okay, so those fixed acids then can actually be buffered by the bicarb. And that's why I was saying the kidneys then are in charge of bicarb. Okay, the bicarbonate ions. So if you see the HCO3, that is the kidneys deal. Okay, So that's where the kidneys and the lungs kind of help each other out. So certain diseases such as diabetic, if they're not treated, okay, they can actually have an increased fixed acid production, which then our body senses that, okay? Our body realizes that's what's going on, and because the respiratory center is in the brain, and our body just automatically compensates by increasing our respiratory rate. So we're trying to blow off, that's what we kind of term it, very technical there, blow off the CO2, okay? So you might have a patient that's in diabetic ketoacidosis, for example, and that patient might come into the emergency room and they look totally healthy, and you're wondering, why am I drawing a blood gas on somebody? They seem to be breathing okay. You may mention or just ask them, do you have a history of diabetes? And chances are they probably do. Usually these people aren't really wearing much oxygen, if any at all, and they're checking to see if they're in DKA, to see if they're in diabetic ketoacidosis. Because if they're not treated properly by getting their insulin in, their sugar levels down, they can, go into a coma eventually. But their body is trying to compensate by increasing their respiratory rate to get rid of the CO2, to help normalize their pH. All right, lots of information. All right, so a buffer system. A buffer then is a solution that resists the changes in pH when an acid or base is added. Okay, so it can kind of go either way. Okay, so a buffer solutions then basically are mixtures of acids and bases, and we classify the buffer systems as either being a bicarbonate buffer system or a non-bicarbonate buffer system. So when we talk about a bicarbonate buffer system, we consider that an open system. Okay, so the bicarbonate buffer system is composed of bicarb, or HCO3, and your carbonic acid. Okay, so let's call it an open buffer because the carbonic acid is in equilibrium with the dissolved CO2, and which is then removed by ventilation. So when the hydrogen ion is buffered by the bicarb, okay, so it's trying to maintain that pH, the product carbonic acid is broken down into water and carbon dioxide. As long as ventilation is going on, it can remove that CO2. Okay, so think of open as your CO2, you're removing the CO2. Okay, you got your cap is off or whatever, open. I don't know, I have weird ways of trying to remember things. And that's kind of what that one diagram was talking about with the hemoglobin, the one that I had to pause for a minute. So this type of system removes lots of acid from our body each day. So bicarbonate buffers have the greatest buffering capacity because of their open system. So on our next slide here, we're talking about the closed system, or the non-bicarbonate buffer system. And this is composed of phosphate and proteins, which include your hemoglobin. And again, that's just hemoglobin then written a different way, or HB. So hemoglobin then is the most important buffer in this system and the most abundant. Okay, so it's more related to your blood. A non-bicarbonate buffer system is also called a closed buffer system because all the components of the acid-base reactions remain in the system. Okay, they are closed as no gas that is available to be removed, to remove the acid by ventilation. So this buffer is volatile and fixed acids. So kind of classifying the buffer systems, then we have bicarbonate, which is the open system, which is in your plasma and involves your plasma and your red blood cells, and then your closed system or your non-bicarbonate system is your hemoglobin, involves your hemoglobin, your organic phosphates, your inorganic phosphates, and your plasma proteins. But I just want to say, add a little something else here that, oh, I think I actually say it here on the next slide. Never mind, I will move on to my next slide. So, just so that you know that these systems don't work in isolation from one another. They're actually intermingled in the same solution, which is your blood. And they are in equilibrium with the same hydrogen ion. Okay, so increased ventilation increases the removal of CO2, causing the blood, then hydrogen ion to fall, which causes the non-bicarbonate buffer to release more hydrogen. So when the ventilation decreases, which ultimately is going to increase your hydrogen because you're not being able to blow off that CO2, this causes the non-bicarbonate buffer to accept more hydrogens, which helps keep it in balance. So it helps offset that acidosis. All right, this is just briefly talking the Henderson-Hasselbalch equation. Okay, so it's the pH of the buffer system. And it basically is describes the hydrogen ion concentration as a ratio of carbonic acid to bicarb. Okay, so this is the formula, how they actually calculate the pH. I'm not going to ask you to memorize that. Just be aware of it, okay? The beauty of it is that it's all figured out with blood gas analyzers. They actually measure the pH of the blood and the PaCO2. So Pa, when you see that little a, that's arterial, okay? So your CO2 level in your blood is actually measured by blood gas analyzers. And they actually use the Henderson-Hasselbalch equation to calculate your bicarb. So it's always a calculated bicarb. We are actually able to measure exhaled CO2, which is PET, pressure of, so P means pressure, your pressure of your end tidal of when you exhale. We put a gas sample line actually in line in an ET tube, or we can actually, which is an endotracheal tube, or on a nasal cannula if somebody's spontaneously breathing, and we can actually detect the amount of CO2 that's being exhaled and kind of get somewhat of a correlation of their CO2 level. We can kind of trend it basically. I know that's a lot of information, but just bite off small pieces and we'll get through it.